These are the last half of the notes from section 6.4, 6.5, and then 7.1 through 7.4. We started the other part in class, but may have not gotten to this section. So I'm going to talk about terminal velocity and the drag force. Basically, we're going to just briefly touch on it here, but we'll get into it more as we get to the end of this whole mechanics unit, and then we'll refresh our memory again before we get to the AP exam. But the idea here is that objects that are moving through a fluid, either air or water, will experience some kind of resistive force. We call that a drag force. And it depends on a variety of things. It depends on the speed of the object, depends on the resistivity of the fluid, depends on the surface area that you have. And as an object moves through that drag force, at some point the weight pulling it down, for example, if we think about falling in the air, will equal the force pushing up. And when that happens, we reach what's called a terminal velocity. And the object then will continue to fall at that constant velocity. It won't speed up or slow down because the forces are balanced. You have an equal up and down force. So that's the idea behind a drag force and terminal velocity. Here is just a clicker question associated with that. It says the terminal speed of a styrofoam ball is 15 meters per second. If we throw that ball straight down with an initial speed of 30, which velocity graph is correct? So we need a graph that's going to get to 15. D here would be the graph that's going to make it for us. It starts at 30 and then it slowly will kind of balance off to 15. All right, and then Newton's third law. This is kind of going to be an introduction or a start to our next set of notes where we're going to connect systems or put objects together. So Newton's third law basically just says that as every force occurs as a member of an action-reaction pair of forces, so essentially as you push on one object, that object pushes back. And those forces are always equal in size but opposite in direction. And the key thing to remember about these forces is that they are the same, but they're acting on different objects. So for example, you've got a big object here and a smaller object here. The force is the same on both objects, but the effect of the force is going to be greater on A because it's smaller. It's got less mass. So here's an example of an action-reaction pair. If we have, let's say for example, A is pushing on B, then we have the force of A pushing on B, and then B is going to push back on A. They will be equal, they will be opposite. An example, hammer and nail. You've got the hammer pushes on the nail, and then the nail pushes on the hammer. So those are the two action-reaction pairs. Same with the gravitational force of the moon pulls on the Earth, which causes the tides, and then the Earth pulls on the moon. And the reason that the moon stays in orbit is because of the gravitational pull of the Earth. So, a car driving at 75 miles per hour east hits a dragonfly traveling 5 miles per hour west. The force is greatest on, and again, this is in Newton's third law, the forces are equal. Same thing here, a semi is traveling west at 55 miles per hour. It collides head-on with a smart car. What's the force greatest on? The force are the same on both objects, because that's Newton's third law. Now, this is a different question. This is now asking for which has the greater acceleration. That is the effect of the force, and clearly the acceleration is going to be much larger for the dragonfly. If you're driving down the road and you hit a dragonfly, you do not notice a change in your speed. But the dragonfly certainly does, because he was going one way and now he's stuck on your car. Same type of question here. Again, the semi and the smart car collide. The forces are the same, but the acceleration is going to be much greater for the smart car because it's just much smaller. Alright, so this again is building into connected systems, and so we've got some rules for blocks, strings, and pulleys. Objects that are attached to each other, for example in this picture with the string, will always have the same acceleration. So whether it be a system like this, or whether it just be two objects pulling back and forth. We assume the string and, for now, the pulley essentially have no mass compared to everything else. And the same string, so for example, this is one string here, will have the same tension everywhere if we're in equilibrium. So here, all three 50 kilogram blocks are at rest if the tension in rope is the tension in rope 2, greater than, less than, or equal to the tension in rope 1. And so here, if we were to think about, so pointer, let's get a pen. So here, if I were to draw the forces, I would have the weight equal to 500 newtons. And then I would have the tension, and if it was just hanging, that would also be 500 newtons. Over here, I have to look at, in a connected system, we look at each individual item. And so again, I would have weight equals to 500 newtons, and I would have T2. And if this thing is not moving, then clearly T2 has to equal the same as T1 here. And so it has to be equal to. Let's get my arrow back. Cool. Okay. Alright, so in the figure to the right is the tension in the string greater than, less than, or equal to the weight of block B. And so if I'm looking at this system, probably the key thing here is that have block A is sitting on a frictionless table. And so again, if I were to be thinking of this force here is going to be the weight of B, and that would equal the tension Alright, so here we have to be careful because clearly the system is going to accelerate. This block's going to pull the whole system down, so this is going to move across, and this is going to move down, and so we're going to have a net force here. Which is equal to the weight of B minus the tension, if I were to draw that net force equation for block B. And so I'd have the mass of block B times the acceleration equals the mass of block B times gravity, that's the weight, minus tension. And so if I rearrange this for tension, I'm going to get basically the weight of block B minus the net force on block B. And so the tension is going to be less than the weight of block B. And then our last slide here, we've had blocks A and B are connected by a massless string 2 and pulled across a frictionless table by a massless string 1. B has a larger mass than A. Is the tension in string 2 larger than, smaller than, or equal to the tension in string 1? Well, the thing about string 1 here is that it has to pull both. Oops, let's go back. String 1 has to pull both blocks, and string 2 only has to pull block B. And so the tension in this first string is always going to be greater. And that ends these notes.